Okay, so we're going to go ahead and start chapter 7 right now. And in statistics, we gather data about a population. And if it's possible, we try to gather data about every single person in the population. It's typically a census. But sometimes we can't afford to, or there's no way that we can possibly gather the data from the entire population. And when that happens, instead of gathering data from the population, we try to gather data from the sample of the population. We then use that sample to help us understand what is happening in the population itself. So we grab a sample of people, we take that information, we get data for them, and then we try and decide what is that going to tell us about the population itself. And we always have a problem with that because the one question I get all the time is, how do we know that sample is really representative of our population? And so that's why the sampling techniques we learned in chapter 4, like the simple random sample, the SRS, or a stratified random sample, or a cluster sample, all these different sampling methods, we want to make sure that we have a good, unbiased sample that should hopefully be as accurate as possible to the population. Now, when we are dealing with data, we have something called a parameter. And a parameter is a number that describes some characteristic of the population. In statistical practice, the value of the parameter is usually unknown because we cannot examine the entire population. Now, we also have something called a statistic. And that is a number that describes some characteristic of a random sample from the population. The value of a statistic can be computed directly from sample data, so the data we get from our sample, and we often use the statistic to estimate an unknown parameter. So as we're working through these, you need to remember that statistics come from samples and parameters come from populations. So distinguishing the differences in notation. So typically we use, when we're working with quantitative or numerical data, we work with means and standard deviations. When we're working with categorical variables, we're working with proportions. But sometimes when we're working with quantitative, we do work with medians and IQR as a measure of spread. And we would use this when our data tends to be skewed, because median and IQR is more appropriate for skewed data. But if our data is pretty symmetric, then we tend to go with the mean and standard deviation, especially if it's close to normal. So what we have is, when we're dealing with populations, so these are for populations, we use the symbol mu, which is the letter U with a long tail in front. That is for the mean of a population. And then we use lowercase sigma, looks like a circle with a little hat on it, I guess, or a line coming out from the top. That is for the standard deviation of a population. But then we also have symbols for samples. So now when we're dealing with the mean of a sample, we're going to have the X bar, and the standard deviation of a sample is going to be SX for the standard deviation of our X value. Now when we're dealing with proportions for our categorical variables, P is going to represent the proportion of the population, and P hat is the proportion of the sample. So again, different notations that we use depending on if we're talking about the population or we're talking about the sample. Now again, we also use percentiles, quartiles, and medians, but again, the ones above are the ones we most commonly use. So our sample problem: identify each bold underlined number as a parameter or statistic. Use the appropriate notation to identify each and determine if the variable is categorical or quantitative. So our first problem: on Tuesday, the bottles of Arizona iced tea filled in the plant were supposed to contain on average 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contained an average of 19.6 ounces of iced tea. So is this a numerical quantitative variable, or is it a categorical variable? And this is, because these are numerical, 20 ounces, 19.6 ounces. This is quantitative. And we're measuring ounces of tea. Now what we want to know is which number is our parameter and which one's our statistic. So which one comes from the sample and which one actually comes from the population. So on Tuesday, the bottles of iced tea filled in the plant were supposed to contain on average 20 ounces. So our parameter on average, so average means mean. So our parameter, the mean is 20 ounces. Now our statistic, so now we're sampling 50 bottles and we found on average, so now the mean of the sample is 19.6 ounces. Okay, next problem. On a New York to Denver flight, 8% of the 125 passengers were selected for random security screening before boarding. According to the TSA Association, 10% of the passengers at this airport are chosen for random screening. So we have numbers, but these numbers actually represent a percentage or a proportion. And we use percentage and proportions for dealing with categorical. And so what are our categories? Screened before boarding, not screened before boarding. Our parameter. So we have a parameter and a statistic. Parameter is for our population and statistic is for our sample. So on a New York to Denver flight, 8% of the 125 passengers were selected for random security screening before boarding. According to the TSA, 10% of passengers at this airport are chosen for random screening. So this is a sample from one flight. So this 8% is our p hat because it's our proportion of the sample. Now, technically we should write that as a proportion. 0.08 is p hat. And then our parameter p is what it should be for the entire airport, which is 10%. Again, we should be writing those as proportions because as we start doing our calculations and all that, we're going to be writing almost all of our stuff as proportions anyway. Okay, how can a statistic be an accurate estimate of a parameter? After all, different random samples would produce different values of the statistic. So we analyze what we call sampling variability. The value of a statistic varies in repeated random sampling. To make sense of that, we ask what would happen if we took many samples. So I take a sample, and then I take a sample, and then I take a sample, and I take a sample, and I look at all those values from my different samples. And I take a look at that information, and that helps me make a decision. So when we do this, we get 3 different distributions involved. And so what we start off with is we have the population distribution. Sometimes we know this, sometimes we don't. And this is the true population. When I take every single car, what's the possible color? Blue and red. Every single blue and red car, what's the proportion? What's my frequency? So our parameter here, p equals 0.5. So half blue, half red. And so this is our population distribution. This gives the values of the variable for all the individuals in the population. Now, our next type of distribution is the distribution of the sample data. So now I'm going to take a sample of 20. I'm going to take another sample of 20. I'm going to take another sample of 20. And I'm going to keep on doing this. So this is the distribution for the one sample. This is the distribution for the another sample, which means this is my statistic. So this is a statistic. This is my statistic. And my statistic is only looking at our reds here. So 11 out of the 20 were red. And 13 out of 20 were red. And so these are all my different samples. And so the distribution of the sample shows the values of the variable for all the individuals in the sample. Again, from the sample. And then what we do is once we've taken all those samples, we put them together in what we call a sampling distribution. And why do we do this? We do this when we know population distribution, so we can kind of figure out how does my sample and my sampling distribution relate to the population distribution. How do I know this can be accurate? And so some key things that we're looking here at these p-hats. So this is, let's see, 0.65. So that's a dot right here. And this is 0.55. So that's a dot right here. And this is 0.40. So that's a dot here. And so this sampling distribution is taking hundreds of samples. And what do you notice about this distribution? It's symmetric. It's symmetric, and look at where our peak is. In fact, it might even be somewhat normal. And our peak is at 0.5. And look how that relationship is to our parameter, 0.5. And so when we take sampling distributions, we find, yeah, not all my sample proportions are 0.5, but when I take lots of sample proportions, look at that curve. And so then we can look at some probabilities that way. And so in class, we're going to go ahead and do some of our own sampling distributions.